All right. Good day to everyone. This is a special class on complex number, and I really believe at the end of these classes, you should be very sound in complex number. So please, can you indicate if you can hear me clearly? Okay. All right. Now, complex number. I really want to put good explanations to this topic in A-level mathematics. So I would really love if you have your pen and your jotter so you can have great notes and solve through as we are solving also. All right. Now we're going to start from the basics of complex number. And as I always say, understanding the basics of every topic in mathematics will always give you an edge in solving technical problems. If you have issues with the basics, there's a very high chance that you would have issues in technical questions. And that's why we love to take time to explain the basics first. So we're going to move steady, ensuring that everybody can participate in the class. So let's start from the origin of complex number. Now, I'm sure complex number has a lot of identification with quadratic equation. So imagine you were trying to solve your quadratic equation. Of course, you understand that the quadratic expression has the highest power to be 2. So we have different quadratic expressions. For instance, this is 1. If we go home to try to solve this, we will get an answer. Sometimes we can use factorization, sometimes we can use computing the squares, sometimes we decide to use graphical methods and so on. Now, in some other cases, we are given another quadratic expression. Take, for instance, we have one like this. And of course, looking at this question also, we will be getting an answer for the root. But take an instance where you have something like this. And you're given this x squared plus 1 equals to 0. How then are you going to solve this quadratic expression? Because if you look at this will end up giving you x squared equals to minus 1. When you have x squared equals to minus 1, the ideal thing to do in mathematics is to take the square root of both sides. Now, if you go on to take the square root of x squared, of course, this will give you x. But could you take the square root of minus 1? Of course, that's not going to be possible. This is what gave birth to the topic we call complex number. Because x squared being equals to minus 1 will not be able to be solvable using every of the general quadratic methodology. I explained last weekend of 3 different situations you can have for your discriminant. I said we could have a situation where our discriminant b squared minus 4ac, we can have a situation where it's greater than 0. We said in this case, it has a solution. We talked about it. We also gave an instance where we have the discriminant being equals to 0. We said this is a situation where it has 2 roots. It has just 1 root, rather, a double answer situation. And then we gave a last one, if you remember, where our discriminant was less than 0. This was when we said it has a complex solution. Well, here is the situation where something like this happens. So we want to talk about complex number. Now, you will leave this class as a guru in complex number if you pay real attention, I can assure you. Now, let's talk about this square root of minus 1. We said x squared equals to square root of minus 1. Don't forget, when we had x squared plus 1 equals to 0, of course, x squared equals to minus 1. And x squared, we could not solve for x. So what we have to do now is to represent our square root of minus 1 with a symbol high. So wherever you see square root of minus 1 now, we will be representing it with I. That's the first identification I want you to have. Now, wherever, this is one thing I want you to hold. There are some things I will tell you to hold, and this is the first one. Represent I with square root of minus 1. Since you could not get a solution to it, we say it has a complex solution when you add square root of minus 1. So this complex solution now, we're going to give it a nomenclature, and that nomenclature will be high. Just note that as the very first thing you're going to note. All right. Now, if you move on from here, if you're trying to find I square, since we said I equals to square root of minus 1, that means invariably I square will be equals to, of course, squaring both sides, I square will be equals to minus 1. I'm sure you all agree with what I did here. I said I equals to square root of minus 1. If I take the square of both sides, these two will cancel the square root and we'll be left with I square equals to minus 1. This is the second thing I want you to take note of. I, number 1, is square root of minus 1. Don't forget where we got that from. After getting to this place where we had x squared equals to square root of minus 1, we said we could not get a real solution for this question. So we went on to know that this was a complex solution, and we named our square root of minus 1 now to be high. We represented minus 1, square root of minus 1 to be high. Now, in solving when I equals square root of minus 1, if I decide to take the square of both sides, I will have I square equals to minus 1. Note that one, so you can always know why we are saying I square equals to minus 1. It's not something that came from nowhere. It came from this solution I just did. I square equals to square root of minus 1. That's very, very vital to everything you'll be solving in complex number. So please never forget that wherever you see I square, you don't have to feel it something very hard. Wherever you see I square, always know it's identified with minus 1. So I square equals to minus 1. You can take that down. So I can write it here that I square equals to minus 1. Now, how do we generally write a complex expression? Now, when we have a number of the form a plus ib, now in this case, a is seen as a real number, b is also a real number. This is what we call a complex number. So the high here is the imaginary side. So this is the general form of a complex number. A plus IB. Just note it. Of course, in some cases, you may have this as a different nomenclature from A and B, but just understand this is just we trying to define the form of a complex number, A plus IB. So in a case like this, we could have, for instance, 2 plus I3. This is an example of complex number. Look at this other one. We can have minus 1 plus I square root of 3. This is also a complex number. This is an example of a complex number. Look at what we're having here. In this case now, we had an whole number, we had an whole number. In this case, we had a negative whole number, whereas in this side we had the square root of a number, which is still a real number. So this is another example. This is how you know a complex number. Now we can also have a situation where we have 4 plus high minus 1 over 11. This is also still a complex number. All right. So we call the A part of this. We say this is the real part. And we always denote this real part with, of course, we can say this complex, let's name this complex number as Z. So our complex number Z now is A plus IB. And this part where we have our A is the real part, whereas this other side is the imaginary part. So we have this A, we can see it as the real part of Z, whereas we have our B as the imaginary part of Z. Imaginary part of Z. So just understand that when we are writing a complex number, we always have these two distinct possibilities where we have the real side and then we have the imaginary side. So in a case like this now, we can see that this is the real side of this particular complex number is 2, whereas the imaginary side is 3. In this other case, minus 1 is the real side, square root of minus 3 is the imaginary side, and on and on and on. Now we can have two complex numbers being equal to each other. So let's say, for instance, we have a complex number Z1 to be given as A plus high B. And let's say we have another complex number Z3 to be given as C plus ID. Now, in this case now, we can say that Z1, sorry, let me have Z2, not Z3. We can say Z1 and Z2 are equal if and only if and only if A equals to C and B is equals to D. These are important questions you can see lots of technical questions from, where they will tell you two complex numbers are equal. So if two complex numbers are equal, if you're given two complex numbers to be equal, just note that the only case for them to be equal is if the real part, in this case, A is the real part here and C is the real part for this, if they are equal, and the imaginary part, B is that of the Z1 and D is that of the Z2, if both of them are equal, that is the only case where you will say two complex numbers are equal. We'll be solving a question on this very soon. And I would love to get your solution as soon as possible. So if you, before I'm done rubbing the ball, you can take the question down and give me my answer. If 4x plus high, open your bracket, 3x minus y, if 4x plus high, open your bracket, 3x minus y, close the bracket. If this is equals to 3, so this is the question, if 4x plus high, 3x minus y, if it's equals to 3 plus I into bracket minus 6. Of course, where x and y are real numbers, so you have to find the value of x and y. So can we have the solution very quickly? Looks like this marker is dim. This is x and y written here. Can you get the solution to this quickly? So if 4x plus high into bracket 3x minus y is equals to 3 plus I into bracket minus 6. If both of them are equals to each other, then go on and find the value for x and y. Do I have an answer already? I just explained the concept you have to use for this. So if you know you have gotten the answer, just indicate very quickly. This is the basics of complex number. Okay, somebody got 3/4 and said y is 19/4. I'm not sure that y side is correct. Can somebody give me a different one? All right, I just told you some few minutes ago that two complex numbers are said to be equal if and only if we have the real part being equals to each other. That means we can only say this is true. This is true, equals to is true, if the real part. Now, the real part for this, you can see 4x here is the real part. Because for you to identify what the real part is, the real part is void of I. That's how you recognize the real part of any complex number. You can see I right here. So this is the imaginary part for the first complex number, whereas this is the imaginary part for the second complex number. So 4x here represents the real part, whereas 3 represents the real part for this second one. And we're going to say two complex numbers are equal if both real parts are equal. That means for this to be the case, 4x must be equals to 3. 4x must be equals to 3. That's number one. And also, if they are going to be equal, 3x, that's the imaginary part now, 3x minus y should be equals to the imaginary part of the second one, that's minus 6. So you have to solve this using, we're having different answers, lots of different answers right here. So we have to use our understanding of simultaneous equation. In this case, we have x to be equals to 3/4. So we have gotten our x value. So we want to go on to find our y value. To find our y value, just put x being 3/4 into this part. So that will be 3 into 3/4 minus y equals to minus 6. That will be 9/4. So this will be 9/4 minus y equals to minus 6. Minus y here equals to minus 6 minus 9/4. What does this give you? Of course, we have this LCM being 4. That will be minus 24 minus 9. That will be minus 33 minus y will be equals to minus 33/4. If you multiply both sides by minus, you'll see that your y will be equals to 33/4. So this means our x is 3/4 and our y is 33/4. So you can see a practical example for solving a question like this where you have equality of complex numbers. All right, let's move on to the next thing now. So we have different operations that can happen in complex number, just as we have in many other aspects of mathematics. So I'm sure you understood what we just did. So that's we're moving on. So we want to talk about addition of complex numbers very quickly. That's one of the operations you have to learn. And I've told you already, if you learn these things, you would get a very big edge when dealing with technical questions. All right, now when dealing with complex numbers, you want to add the real parts of the complex numbers separately and also add the imaginary part. Now, but one of the basic things we want to discuss under the addition of complex numbers is the properties, which is very key. Understanding the properties of additions under complex numbers is very important, as this could be one of the difference that will come between a technical questions and a simple question, being able to identify different properties. So the first property we'll be talking about is the closure property. Very, very important. Now we have Z1. Let's assume we have a complex number Z1, and let's say we have another complex number Z2. Of course, let's just call this A plus high B, the general form, and let's call this second complex number C plus high D. All right. Now, if you wanted to add these two together, Z1 plus Z2, all you have to do is to add the real part, which will be A and C. So you go on and do A plus C, then you go on and add the imaginary side. That will be B plus D. So this is the whole concept. An example could be, let's say our Z1, okay, let's just say we have two complex numbers. Let's say we have 2 plus high 3, and we wanted to add this with minus 6 plus I5. How do we go about this? As you can see, all you have to do is to add the real part. That will be 2 plus minus 6. 2 plus minus 6. And then you go on to add the imaginary side. That will be 3 plus minus 5. Sorry, plus 5. So this will finally give you minus 4, because 2 minus 6, that will be minus 4 plus high 8. So this is just the basics of additions of complex numbers. Now, but let's talk about the closure property. I'm sure you understand the use of the word closure when we're dealing with mathematics. When you say closure, that means being enclosed. So additions of complex numbers, they have closure property in the sense that whenever you're done adding two complex numbers together, your result will always give you a complex number. That's just the basics of closure property. That means the result is enclosed inside the whole definitions of complex number. So we have this as the resultant of addition of these two complex number. And if you can notice, this is still a complex number. So we say the sum of two complex numbers is a complex number. That's closure property. Now, another property is the commutative property. Commutative property. Under addition, don't forget, that means the meaning of commutative, that means we can say Z1 plus Z2 will also be equals to Z2 plus Z1. So complex numbers are commutative when it comes to addition. Another property under addition of complex number is the associative property. So we have, imagine we have three complex numbers now. That means we have Z1 plus Z2. Now we're done with this, then we go on to say plus Z3. I'm sure you understand the associative laws in mathematics. When you have something like this, I want you to understand that additions of complex numbers are associative. That means if you had three complex numbers together following this format, if you had the first two complex numbers, Z1 and Z2, then you go on to add the third one. It will still give you the same answer if you added the second and the third, and then went on to add it with the first. So it's associative. That means complex numbers additions are associative. Now, one other property under complex number is the existence of additive identity. Additive identity. You know, we talked about identity in our previous class, and last weekend's class. And I told you that one of the major features of identity in mathematics is it's more like a mirror. Identities always reflect back whatever you use it on. So that means, for instance, if I have under complex number now, if I have, we used to call we said the existence of additive identity. But let me define that, because when we say additive identity, we're talking about zero complex number. You know, when we were dealing with matrix, we said identity was 1001. I'm sure you remember that, where we had 1001. All right. Now, but for complex number, don't forget this is not matrix. So what we have is what we call the zero complex number, where this is a zero complex number. Actually, we denote a zero complex number with the word zero. So it will have the real part to be zero, and the imaginary part will be zero also. So if we go on to have to check the identity, this is what we call the identity complex number, the additive identity. And this is how it features. If you say z plus 0, z plus, that means the additive identity here, which 0 is represented by the additive identity, you will always get z back, which is the important feature of identity. When we're dealing with matrices, we said a times a with I will always give you a. The same thing goes under additions of complex number. If you have a complex number plus an additive identity, which this is an example of an additive identity, you will always get the complex number back. And then the last but not the least is it has also what we call an additive inverse. Additive inverse. Well, in the case of additive inverse, we have this is what we call an additive inverse under complex number. We have minus a plus I minus b. So imagine you had your z as this, as what we have here. Then this is what we will call the additive inverse. And when you have z, of course, we always denote this as minus z. We always denote the additive inverse as minus z. These are just properties. I'm just trying to give you the properties so that in case you are being tested around this, you don't have any issue. So if you have the addition of a complex number with its additive inverse, you should always get 0 as your result. So these are just the few properties we'll be discussing on complex number. I just needed you to know this so that you don't ever come across this and have any issues. All right. So let's run quickly to difference of two complex numbers. Well, we don't have to waste much time on that because just the same way we had the addition is the same way the subtraction goes. So for instance, let's say you have Z1 and Z2 as given below. We can say Z1 minus Z2 will be equals to Z1 plus minus Z2. Of course, it's still the same thing as Z1 minus Z2. Now, let's say we have an example where we have two complex numbers. Let's say we have 6 plus 3i. We'll be going into solutions very soon. I just needed you to know all these basics so that you don't ever stumble along the way. So if we are trying to subtract these two complex numbers from each other, we just have to say you see Z1 plus minus Z2, and don't forget what we said about the addition. So we'll be having the real with the real, and then the imaginary with the imaginary. So this will obviously give you, in a case like this, will be 6 minus 2, that will be 4, and this will be plus 4. I'm sure you can see that because this will be 3 minus 1 plus 4i. And if you have another one, let's say 2 minus I, these are just basics that I want you to at least see how it's being done. Just assuming you don't have any prior knowledge on this. So if you have this one, of course, subtraction, this will be, in the end, this will be minus 4, real, then you subtract the minus 3, that'll be minus 4i. So I'm sure this is clear. Let's run to the multiplication part of complex number. multiplication of complex number. These are key to all the different other solutions you want to be doing. Once you understand how to do all these things, you will not go wrong. So let's attempt to multiply two complex numbers together. Let's say we are trying to multiply Z1 and Z2, right? So we have Z1 and Z2 right in front of us. Let's try and multiply these two together. Now I'm going to do it the traditional way, and I'm also going to give you like a proven fast way which you may want to use. So if you have this complex number Z1 and Z2 right in front of us, and you're told to have Z1 times Z2, Z1 times Z2, of course, the normal way you used to do your algebra multiplication will work, but please pay attention and see how it will work perfectly. I will try and do it this traditional way, and I will also give you a faster way to do it by just using terminologies there. Look at this. If you want to do this using the normal traditional way, you want to say A times C, that will be AC. You want to say A times ID, that will be IAD. Then you want to say I times C, that will be plus IBC. Then you want to say IB times ID. Now that will be plus, pay attention, I, that will be I square, then BD. All right. If you don't pay attention to I times I being I square, that may be the beginning of a colossal mistake in your multiplication. Now, look at what we have here. What you have here, I square. What did we define I square as when dealing with complex numbers? We defined it as -1. We said I square equals to -1. So looking at I square in this place, you can see that we can easily change I square to -1. All right. So you can, if we try to collect like terms here, you can see we have AC minus BD, then plus AD plus IBC. Now, this brings me to the nomenclature I want to teach you that will be very fast, which is you just wrapping this all as one, and then having this, sorry, I omitted the high here, and having the high into bracket and have AD minus, or sorry, plus BC. Now, this is what I mean by a fast way. Look at what we have here. Of course, you can see I use the traditional way. The main key is to never forget your high square is -1. That's the main key. Now, looking at this long multiplication we did, you can decide to just understand how this happens and always use this. So what I would always know is that when I'm trying to multiply any two complex numbers, I can see that A here represents the real of complex number 1, C represents the real of complex number 2. So I know that I want to say real of 1 of the first complex number, real of second complex number, minus, I know that B and D are both, B is the imaginary part of the first complex number, while D is the imaginary part of the second. So I want to say the imaginary of the first one times the imaginary of the second one. I want to put that in one bracket, and I want to say plus high into bracket the real with the real of the first, imaginary of the second, plus imaginary of the, that means in short, just make the other two. Real of the second, that means real of the second, imaginary of the first. So anyhow you want to place that, it doesn't really matter. Don't forget, this thing is commutative, so multiplication C and D doesn't really matter. You can have it as CD, sorry, you can have it as real of second, imaginary of first. So anyhow you want to see it. So this will give you an edge. You don't have to waste time at all. You just have to, if you understand how these things go, you don't have to go through all the long process. I will just pick all my values and get my answer very quickly. All right, now we can move to the next thing, and that is divisions. Or let's talk quickly about the properties under multiplication. Number one, we have the closure laws. The closure law works under complex numbers multiplication. And don't forget, let me remind you what closure means again. Closure means your final solution is enclosed within the whole concept of what you're dealing with. So the product of two complex numbers is a complex number. That's what closure means. So after getting this answer as my answer, this is still a complex number. So that's why we say the closure complex number multiplication is closed. Number two is the commutative law works under multiplication. So Z1 times Z2 is the same thing as Z2 times Z1. Note all these things so that you would always have the edge over any question you are given. Now, also don't forget, the associative law works here also. That means associative law says Z1, let's say we have three complex numbers, multiplied by Z2, multiplied by Z3 is equals to Z1 multiplied by Z2 multiplied by Z3. In this case, I'm sure you understand this from your binary operation class. So if you decide to multiply the first two complex numbers, get an answer, and then multiply that one with the third one, it's still going to be the same thing if you multiplied the second one and the third one, and then you came back to multiply that result with the first one. That's the meaning of associative law under complex number. So I want to run to what we call the multiplicative inverse. This will really help you. This is one of, if you are not paying attention to anything I will say, make sure you pay attention to this. The multiplicative inverse is very key. Very, very key. So we have, of course, before going to multiplicative inverse, we have the existence of multiplicative identity. These are questions that you can see in your objective questions for you to find to talk about the laws that holds in multiplicative aspects of complex numbers. So always make sure you note all these things. They're not a waste. Note all these things so that you can always ace every aspect of your questions. Now, the multiplicative identity, don't forget what identity. Whenever you hear the word identity in anything, just know that it serves as a mirror. So that means in this case, we have something we call the multiplicative identity. I talked about the additive identity. Under the addition rule of complex number, the additive identity, we termed it 0. And we said it was equals to 0 plus I0. Don't forget that. But under multiplication, we have what we call the multiplicative identity. And that one, we term it as 1. We term it as 1. And it's equals to 1 plus I0. Note it. This is it. It's only 0 here. This is the multiplicative identity under complex number. And how it functions is that if you have a complex number Z and you multiply that complex number with its multiplicative identity, of course, once you are dealing with identity, always note one thing: you will always get the complex number back. So this is one of the properties of multiplication under complex number. Now, the last but not the least, not the last but not the least, second to the last, is what is the existence of multiplicative inverse. So multiplicative inverse is where you need to pay real attention now. Now, you should understand what multiplicative inverse always does. We talked about additive inverse. Additive inverse of complex number. We said under additive inverse, when we had additive inverse, we had Z plus minus Z. We said there was an additive inverse of minus Z. When this video is released, you can go back to check for all I said there. When we have additive inverse, we always get 0 as our answer. But under multiplicative inverse, when we have Z, if you multiply Z with its multiplicative inverse, which is always sometimes seen as 1 over Z, sometimes you can write this one as Z raised to power minus 1. Anyhow you see these two things, either 1 over Z or Z raised to power minus 1. Once you multiply Z with the multiplicative inverse, you should always get the value of 1. That's one of the property under multiplication of complex numbers. So it's the multiplication of a matrix which is and multiplicative inverse will always give you 1. So the next question to ask yourself is, what is this z raised to power minus 1? What is this multiplicative inverse? It's a bit complex, so look at it this way. Z raised to power minus 1, which is the multiplicative inverse, is equals to, let's say for instance, this is the complex number we're dealing with, z1 here. So if we were dealing with this one, it would be a different terminology to be using. So I'm using that of this particular z1, which is a plus ib. So if I wanted to find the multiplicative inverse of this z1, let me write z1 here. So it will be a over a square plus b square. You'll be seeing this in the equation very soon. Plus I minus b. You need to write this down and know it. Just find a way to know it. So this is the multiplicative inverse of a complex number. You can see it. This is it right here. The multiplicative inverse of a complex number. So we have, you notice it, we have the real part plus minus the imaginary part, and then the denominator is always the a square plus b square. So note that, and you will see how this works very fine. Now the last but not the least, properties under multiplication in complex number is what we call the distributive law. I don't know if you have seen this anywhere before, but let me just try and bring this to you so that in case you see this in an objective question, you would not omit distributive law as one of the properties under multiplication. It's actually one of the properties. So you should be very vigilant to pick your options the right way. So multiplicative law says that if you have a complex number like this, and z1 times z2 plus z3, notice the operation going on. Two complex numbers are being added, and then you are multiplying the result with z1. Under distributive law, under complex number, this should give you and should be equals to z1 times z2 plus z1 times z3. That's distributive law. And then the same goes for the other side where it was probably a different case where we have z2 now plus z3, sorry, z1 rather, plus z2, or look at the way this goes now, being multiplied by z3. Now, this should obviously give you z1 times z3 plus z2 times z3. So this is what we call distributive law. So you can just note it so that you can understand all these different properties. So under multiplication. So now let's run to divisions of complex number, division of two complex numbers. Please make sure you are following what I'm explaining, because when we are solving questions, these are some of the things that will give you an edge over any kind of question. No, addition is not, you can't talk about addition being distributive, all right? Because we don't have, we don't have that law being handled there, because distributive always involves more multiplication also. I don't know if you understand what I'm saying. So note all these different laws that are in existence when dealing with complex numbers and understand what they say. I talked about multiplicative inverse now. Please note all these things. I didn't try to explain how you got it. I just gave it to you. So note them somewhere so that when you need it, you will need it very soon when we're dealing with any question. So when you need it, you will be able to call it handy. Now, let's run quickly to divisions of two complex numbers. So as I said before, let's assume I have the two complex numbers as z1 and z2. All right. Now, how do you divide these two complex numbers? Now, do you see exactly what I said some few moments ago? I talked about the use of multiplicative inverse. Now, if I wanted to divide these two complex numbers, z1 and z2, you will need the concept of multiplicative inverse to prosecute this easily. Now, there may be other methods, but multiplicative inverse comes in very handy here, because look at z1 over z2 can also be written as z1 times 1 over z2. So obviously now, you see that means you just need to go and find the multiplicative inverse of z2 and multiply Z1 with that multiplicative inverse. So you understand the reason why I wanted you to understand multiplicative inverse. So let's try something quickly. Let's solve a question very quickly because of time. So let's say we have a Z1 as 6 plus 3i, and we have a Z2 as 2 minus I. So please, can you quickly go and help me to find the multiplicative inverse of Z2? Can you do that very quickly? I'll be doing mine also. All right. So I will be doing mine, but can you quickly go and solve the multiplicative inverse of Z2 using the formula I just gave you? Can you do that very quickly? So please just keep doing that while I'm doing mine. Make sure you focus on yours, and then you will be able to use mine as a way of correcting yourself. So now, if you look at the formula I gave before on multiplicative inverse, I said it was a over a square plus b square plus I into bracket. Okay, I don't need the bracket there. Let's just have minus b over a square plus b square. Now, if I want to do the multiplicative inverse of 2 minus I, and my a here is obviously 2, my a here is 2, and my b is minus 1. All right? Note this is a, this is b. B is minus 1. Because don't forget, when I had a plus bi, and a plus ib as I had z being equals to a plus ib. That means b is minus 1 and a is 2. Now, if you apply this to this something, we have 1 over z2, which is sometimes also seen as z2 minus 1. I told you any one is okay. It will be given as, we would have our a to be 2 over a square plus b square. That will be 2 square plus minus 1 square. Then plus I into brackets. We have, there's a minus there. So this will be minus, then b is now minus 1, minus 1. Everything over 2 square plus minus 1 square. All right. Now, looking at this now, this will be equals to, this whole thing is this 4 plus 1. 4 plus 1. That's actually 5. So this will be 2 over 5 plus I 1 over 5. So we can write this easily as 1 over 5 into 2 plus I. So that's just the way we're going to solve for the, you can see how we're able to get the multiplicative inverse very easily by just fixing this into a formula we already know. So now the next step, this is not the final step, because the next step is for us to now go on to have, because we're told to divide the 2. And I told you that to divide the 2, we have to multiply z1 times the multiplicative inverse. This was z1. So to find z1 over z2, I will have to go on to have z1, which is 6 plus 3i. And then I will multiply this with the multiplicative inverse of z2, which is now 2 plus I over 5. So can you go on and do this multiplication very quickly? You can go on to do it very quickly, so you can flow along. I will do mine also here. So I already taught you a very fast way of multiplying these two things together. I would prefer to write it this way, and I don't know which one I should use, probably the faster way, or I should just go on to do it the traditional way. Whichever one, please just go on to do what works for you. This will be 2 over 5 plus I over 5. I1 over 5 is the same thing. So if I want to get my final answer now, I want to go on and Just look at it. Let me clean this up. All right. Now, if you look at what we're doing now, you can go on to open it the traditional way and just open everything the way you want to. That means you want to do 6 times 2 over 5. That will be 12 over 5. Then 6 times minus 1 over 5i. That will be plus I 6 over 5, because 6 times 1 over 5 will be 6 over 5. Then 3 times 2 over 5. That will be plus 3 times 2. That will be 6 over 5 with the high. 6 over 5. Then I want to do 3 times 3 times 1 rather. That will be plus I squared. Then 3 over 5. All right. So this is me using the traditional way, just because I'm sure many of you are probably not mastered. You've not mastered the fast way I explained. So let's see what this gives me. This turns to minus 1. So minus 1, 3 over 5. Now I have 12 over 5. I can have plus I into bracket 6 over 5 plus 6 over 5. All I'm doing here is raw algebra. So I have 12 over 5. This is minus 3 over 5, because minus 1 times 3 over 5 will be minus 3 over 5. Plus I can decide to factorize 1 over 5 out. So I have 1 over 5, then I will have 6 plus 6. Anyhow you want to do your work, there is no issue again. All right. I'm sure you guys are working yours and you are able to. I'm sure you're working what you have to work, because that's the basics of all this. You have to get your own hands doing all this. So if you do the LCM of this, this will be 9 over 5. This will be 9 over 5. And this will be plus I1 over 5, 12. So we can easily say, because you can see 1 over 5 is common to both, so we can factorize 1 over 5 out and give our final answer to be 9 plus 12i. And that's just it. So you can see this is the division for z1 over z2. Can you see the answer? And just to cap it up, remember the way we moved. For us to do z1 over z2, we had to go on to for us to have z1 over z2, we first did z1. We first did the multiplicative inverse of z2. Then we went on to multiply that with z1 and we got this answer. So it's quite very, very simple. I'm sure you understand what we're doing. So let's quickly talk about the powers. Sorry, can you still hear me? I want to be sure I'm still conveying this message clearly to everyone. Can you still hear me? Please, can you indicate if I'm still being very clear? Is the rain disturbing? Should we continue from here tomorrow by 6 o'clock, or should we keep on going? What do you say? Okay, I think before we go, let me I want to just, if we have, okay, the rain is disturbing. So am I able to communicate to you, or do you, okay, network is bad. Okay, you know what we're going to do, because of the issue of, let's meet, can we meet by 6 p.m.? We meet by 6 p.m. tomorrow. So because we want to go into the core of the real core of complex numbers and solve lots of questions on it. But before, I want you to make some attempts to these questions I want to give you quickly. But we'll still have our class by 9 p.m. We'll be solving quite a number of questions. tagged exam preparation. So we want to solve various questions from various topics. All your topics in 001, we want to pick lots and lots of questions from those sites, and we want to solve a lot of questions. So 9 to 10 every day. We'll keep on going with that. But for this complex number classes, these 6 p.m. classes, we'll be talking about calculus very soon. So I want to see how to talk about all these topics in such a way that nobody should have issues with them anymore. So let me give you some questions to solve, and I want to really see how you fare with them. Are you guys ready? Okay, so okay. So I want to give you questions to solve, and please, that's one of the first thing I'll be interested in asking tomorrow. And look at these 3 questions. We have 4 minus 3i. We have square root of 5 plus 3i. And then we have minus I. I want you to find the multiplicative inverse of these 3. Now that's not all. Then I want you to give me the solution to these 2 questions also. I have 1 over 5 plus I 2 over 5. Sorry, I don't need to put this in brackets. This is how I should use the bracket. I want you to make the subtraction of these 2 complex numbers. 4 plus, please, I want to see this in every note. Please make sure this is in your note, please. Make sure this is in your note. Let me put number 5 here. Oh, I should not always be using brackets. So we have this, and then it concludes with minus. And we have minus 4 over 3 plus I. So look at these 5 different questions. The first 3, you're supposed to find the multiplicative inverse of the first 3. 4 minus 3i and this and this. Now number 4, look at the operation you are told to do there. You're supposed to subtract these 2 complex numbers. And look at for this number 5, you're supposed to do this and then do this. So we'll talk about the solution first thing first tomorrow. Same time, same venue. Please come on time because we have to. I suppose we can conclude, if possible, complex numbers tomorrow, and I think we will go into another, maybe calculus or something. So by 9 p.m. we're meeting for an all important class. We're going to solve lots and lots of questions on several topics, binary operation and every other one in between. So guys, thank you very much for joining. I hope to see you by 9 p.m. Take care of yourself.